we've saved the best application of the snake lemma for the last lecture of this week. This is called the Mayer-Vietoris sequence, and what it really does for you is it allows you to compute homology of a large, complicated simplicial complex, sort of in parallel, as if you were, doing it on a GPU. You can chop it up into several pieces, send the pieces off to different places, and then reassemble the result to get the homology you want, with the benefit being that no single processor had to work too hard. Okay, so this is what we're going to try and do, and the only sort of algebraic prerequisite for this, besides the snake lemma, is the following definition. If C, D, and C prime, D prime are chain complexes, then their direct sum, which is usually written with direct sum symbols, C plus C prime, D plus D prime, is the new chain complex whose k-chains, you get no points for guessing, are the direct sums of the k-chains of the two pieces, and the boundary operator, which goes from the k-chains to the k-1 chains of the direct sum, is just a block matrix. It sends the C chains to the C chains using the boundary operator you have. It sends the C prime chains to the C prime chains using the boundary operator you have, and there's no cross-contamination. It just completely splits into these two things. And because there's no interference between the C and the C prime, the way this boundary operator has been defined, it is easily checked that the homology, the kth homology group of C of this direct sum chain complex is just the homology, the individual homology groups direct summed. If you did the computation, the kernels of dk would all sit in the upper left quadrants, the images would all be in the upper left, and the dk prime stuff would all be on the lower right. They never interfere with each other, so things are just completely decoupled. And this is just a sort of bookkeeping way of combining two chain complexes into one without interfering with the homology groups. Okay, so what is the Mayer-Vietoris sequence good for? The Mayer-Vietoris sequence is good for the following scenario. So K is a simplicial complex, which I want you to think of as sort of a terrible, evil, large, complicated monster of a simplicial complex. And it has subcomplexes, and it's partitioned into them. So it's decomposed as K equals L union M, where L and M subset of K are subcomplexes. Okay, the intersection of two subcomplexes of simplicial complexes is always a subcomplex. If this is not obvious to you, you should sit down and try to prove it. The key is that if you have a simplex in L and that same simplex in M, then its faces have to be in both L and M, therefore in the intersection. So it's not a very hard proof to write down. Okay, let I be the subcomplex given by the intersection. So I equals L intersection M. Okay, so K is the union of two subcomplexes that might intersect in some complicated way. The idea is that you can compute the homology of K by figuring out the homologies of L, M, and I. So you can, all of them are strictly smaller than K. So this is the distributed part, where you can split things up into smaller pieces and figure them out. What the game is the same one that we played in the previous lecture. We need a short exact sequence of chain complexes from which we produce a long exact sequence of their homology groups. We don't quite have access to a short exact sequence of chain complexes. What we have is the chain complex of I, the intersection, which we know will include into the chain complexes of both L and M. And we know that these two in turn will include into the full chain complex of K. And because everything here is inclusion, this is a commuting diamond in the of chain complexes and chain maps. Any path from the I chain complex or the K chain complexes just include the I chains into the K chains. It doesn't matter whether you factor through L or M. The end result is going to be the same. Okay, so from this we want to produce a short exact sequence, which, if you remember, requires 3 terms, not 4. And what the goal is to create a short exact sequence, and we'll do it by globbing these two annoying terms together into one by passing to their direct sum. So here is the claim, is that there exists a short exact sequence of chain complexes of the form you have the I complex at the beginning. It includes into this direct sum of L and M. M, which somehow surjects into, the chain complex for K. And let's call this inclusion map iota as before, and this map pi. So what we're claiming is that there are chain maps iota and pi that will turn this into a short exact sequence of chain complexes. And so the proof of the claim is to define iota and pi and check that they do the job. So define iota. So it has to take a chain C, which is some linear combination of simplices in the intersection I, and then it's supposed to spit out a chain in the direct sum, which is just a chain in L and a chain in M. And this is the most natural thing you could do. This is just send it to C. And why is this the most natural thing you could do? Well, every chain in the intersection is built up of simplices. The simplices happen to be in both L and M, so of course you can send that chain to 2 copies of itself, one in L, one in M, and this is a perfectly good chain map because boundaries are respected. The slightly trickier one is to define pi. Now, pi is going to take a chain in L and a chain in M and produce a chain in K. And you take alpha and beta and you say beta minus alpha. And now the claim is that this gets the job done. It's not bad at all to prove that the image of iota is in the kernel of pi, because if you see what happens here, you're going to take 2 copies of the same chain going into L and M, and then pi is going to subtract them and produce a 0 chain in K. So that's pretty straightforward. It's a little bit harder to show that pi is surjective. And the reason it turns out to be surjective is that K is a union of L and M, these 2 subcomplexes. So any chain in K can be written as something in M plus or minus something in L. So because every simplex that shows up in K is either in L or M. So that's easy. So really the part that's going to give you a little bit of trouble maybe is showing that the kernel of pi is exactly this image of iota. But again, that's not so bad. If you're in the kernel of pi, you have to be, beta minus alpha has to be 0, so beta has to be equal to alpha, which means you must be in the image of iota. Okay, good. So that's done. And now the minute you have the short exact sequence of chain complexes, you're allowed to define. So you're by the snake lemma. There exists some family of connecting homomorphisms, this time going from the chains in K, sorry, not the chains, but the homology of K, to the K minus first homology of this intersection I. And they fit into the Mayer-Vietoris long exact sequence. So which we will now define. The Mayer-Vietoris exact sequence associated to the decomposition K equals L union M, with I being used to indicate the intersection, is so you take it's an infinite sequence, so you take the K chains in I, you get the induced map on homology to the direct sum, then you take the map induced by pi, so this is HK iota, this is HK pi to L, and then you take BK and you get HK minus 1I, and the story continues again. This is the Mayer-Vietoris long exact sequence, and this is an extremely powerful tool for trying to figure out homology of complicated spaces, provided you can break them up into subcomplexes that are relatively easier to understand. And my favorite example of this, which is written up in the notes nicely, so you should take a look, is you can simultaneously compute the homology groups of the hollow simplices, all of them at once, which is sort of amazing, right? We're doing an infinite amount of work at once by computing all the homology groups of all the hollow simplices across all possible Ks in homological dimension I at once. And the trick, or the insight, really, it's not a trick, is to write this as a union, K union L, L union M is how we're writing these, L union M, where L and M are have the homology of a point. Both of them have homology, which is F if dimension K is 0 and 0 otherwise. While the intersection is the hollow simplex of one dimension less. And here's the picture, and we'll end with the picture. So I guess this is the picture for the hollow 3 simplex. So it's not filled in, but all the sort of two-dimensional faces are there. And you decompose this into two pieces. The first one is a cone. So this is just the top vertex. So this, let's call it L. This looks like it's the whole thing, but we're missing the bottom cap. So the bottom cap is this, just that I, and then here is M. Okay, M and L are contractible. We showed this in the when we were talking about homotopy in week 2. Therefore, they have the homology of a point as indicated upstairs, and I is of course the same as the hollow simplex, the hollow 2 simplex. And so what happens is the Mayer-Vietoris sequence looks something like this. If you remember, you have hk of I going into hk of L direct sum hk of M, which then goes into hk of K, and then it goes into hk minus 1 of I. And so if you shift your perspective slightly, you get to sandwich things between hkl direct sum hkm. So you go to hkk. This is just a shift, so we're starting from a different point. It's an infinite sequence, so just imagine we've slid one level forward. hkk, hk minus 1, sorry, not m, that's k, that's k minus 1 I, and then k minus 1 L direct sum k minus 1 M. Okay, the advantage of sandwiching it between the direct sums is that for all k strictly bigger than 1, this term is 0, and that term is 0, which means that this map dk is actually an isomorphism. And so if you know the k minus first homology of the k minus 1 holosimplex, then you learn the kth homology of this holosimplex. And this is not just in index k, right? So we can write this as, in order to avoid confusing indices too much, let's just write this as the ith homology. So for all I bigger than 1, we can write this as I, everything is I. And okay, so the sandwich between 0 and by exactness, the map in the middle has to be an isomorphism. And so if you know the homology of the hollow k minus 1 simplex, then you automatically inherit the higher homology groups of the k simplex. And if you, the hollow k simplex. And if you put all of this together, the homology of the hollow k simplex, this is the homology of the spheres, because if you remember, this is its geometric realization is homeomorphic to a sphere. This turns out to be a copy of the field if I equals 0 or k minus 1, and it's 0 otherwise. So that's the music of the spheres for you. See you next week.